Look up. The night sky stretches endlessly above you, painted in deep velvet black and scattered with a billion cold sparks of light. Some are sharp and bright, others faint like tiny whispers on the edge of vision. You might notice one star twinkling more insistently, while another burns with a steadier glow. The air is still. The silence feels endless, as if the world itself is pausing to remind you of how small we are compared to all that space. So, before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And if you're tuning in from somewhere far across the world, share your location and your local time in the comments. I'd love to see just how wide and connected our little community can be. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. When we start thinking about how big the universe is, our minds instinctively grab at something we can relate to, something that feels solid and measurable. Our lives are full of distances we understand without even needing to calculate. We know how far it is to walk across the room, to drive across town, or to fly across the ocean. We've been trained, in a sense, to navigate within human-scale spaces. 100 steps, 1,000 miles, 10,000 kilometers. These are distances our minds can bend around. But the moment we look up at the stars, the scales start to wobble. They stretch out like elastic, growing longer and longer until numbers lose their meaning. Think about it this way. If you hold out your arm and spread your thumb and pinky finger as wide as you can cover about 20 degrees of the sky. In that little spread of your hand, just a small patch of darkness, there are hundreds of stars. And in some parts of the sky, if your eyesight is sharp and the night is clear, you might even be covering entire galaxies, each containing billions of stars. Imagine trying to hold that in your mind. Billions of suns in a space smaller than your hand against the sky. It's no wonder that when people first began to measure the universe, they struggled with words. They compared stars to candles, the sky to a dome, the planets to wandering gods. The metaphors were small because human lives are small. But slowly, through centuries of looking, building tools, and daring to ask bigger questions, humanity stretched its measurements outward. Step by step, we've tried to wrap our minds around scales that resist being wrapped at all. And yet, the best way to begin is not with giant galaxies or unthinkable distances, but with something close and familiar. The idea of scale itself. So let's shrink things down. Imagine you are holding a grain of sand between your fingers. That grain might be 0.5 millimeter wide. Small, yes, but easy to see and measure. Now picture stacking 100 of those grains side by side. They would stretch only 5 centimeters, barely the width of your palm. That's our first step, from one grain to a line of many. Now let's say we blow that up to the size of a football field, 100 meters long, goalpost to goalpost. For you, walking across it might take a minute or two. For a grain of sand, that's enormous, thousands of its own length. Already, we're playing with the idea that something tiny can become massive, depending on what lens you use to see it. That's exactly what we're going to do with the universe. We're going to stretch, shrink, and reframe. At one scale, the moon feels impossibly far away. At another, it's our backyard neighbor. At one scale, galaxies are giants. At another, they are small dots clumped together into patterns that make our largest numbers shiver. But before we even leave Earth, pause for a moment. Think of the place where you are sitting. Maybe it's a chair, a couch, or a bed. That space around you, the walls of your room, the ceiling above you, feels safe, familiar, containable. If you walked across it, you'd take only a handful of steps. If you stretched out your arms, you might nearly touch both walls at once. That's one kind of space, human space. Step outside, and your neighborhood opens up. Streets and buildings, parks, rivers, maybe mountains in the distance. Distances grow longer. Your body knows them, but they take more effort. A walk becomes a journey. A drive becomes a necessity. And beyond that, your city, your country, the globe itself. These layers stack and expand until the place you began, Your little room feels minuscule. That's still our home scale, just stretched wider. Now, look up again. The moon hangs at an average distance of 384,000 kilometers. If you drove at highway speed, non-stop, you'd need more than 5 months to get there. And that's only the first step away from Earth. The Sun, by contrast, is 150 million kilometers away. That distance feels so staggering we give it a new name. An astronomical unit, or AU. We use it as a kind of cosmic measuring stick because saying 150 million kilometers every time would drive us mad. But pause again. 150 million. We use numbers like that in national budgets or global populations. We can just about imagine 7 billion people on Earth, even if we'll never see them all. But 150 million kilometers of empty space, that's not a crowd of people. That's an emptiness so wide we struggle to picture it. And yet, compared to the universe, the Sun is right on our doorstep. Our whole solar system, from Mercury whipping around the Sun to Neptune crawling at its edge, is tiny compared to what lies beyond. But we're not there yet. Right now, we're just learning how to scale our imaginations. Because to answer the question, how big is the universe, is not a matter of one simple number. It's a matter of learning how to stretch your sense of space over and over without breaking it. Like an accordion, your mind must expand outward and then settle back inward, holding the tune of both the small and the large. You must be able to stand in your room and know it as your world, then picture the Earth and see it as just one grain of sand in an endless desert. This first step, then, is about preparing your mind. We are not just measuring with rulers and light years. We are learning to see with two sets of eyes at once, the close and the far, the tiny and the vast, the human and the cosmic. So as we continue, remember that grain of sand. Remember your room. Remember the football field. Each time we take a step outward, hold those images like anchors. Because if we leap too fast, we'll lose the thread entirely. But if we go slowly, grain by grain, step by step, the vastness begins to take shape, not as a blur of meaningless numbers, but as a story. And stories, unlike statistics, have a way of fitting into the human heart. The universe may feel impossibly vast, but the best way to step into it is by starting small, starting with us. Because the question of size always begins with comparison. We understand big only because we understand small, and the most familiar scale we know is the human one. How big is a person compared to the cosmos? It sounds like an easy question, but it is actually the foundation of every measurement we make in astronomy. Stand up for a moment, stretch your arms. The average human body height is somewhere between 1 meter and 2. In cosmic terms, that's vanishingly tiny. But for us, it's enough. 1 meter is the length of a step, the span of a reaching arm, the width of a doorway. That's our base unit, the anchor point for our sense of scale. Now imagine shrinking yourself down to the smallest details you can perceive. The cells in your body are micrometers wide. Your red blood cells are about 7 microns across, 7 millionths of a meter. That means you could line up about 14,000 red blood cells across the span of your hand. You are, in a sense, made of countless little universes of their own, each cell buzzing with machinery that would take an entire book to explain. Go even smaller, atoms. Each one is about 1/10 of a nanometer wide. That's 1 billionth of a meter. The jump from the human body to the atomic scale is already astronomical in reverse. Our minds wobble when trying to picture something that small. And yet, those atoms form molecules. Molecules form tissues. Tissues form you. You are a stack of scales already, a living reminder that vastness is relative. Let's flip the telescope the other way now. You are about 2 meters tall. The tallest trees in the world, giant sequoias in California, reach around 100 meters. That's 50 of you, stacked one on top of the other. Tall enough to pierce clouds, yet still bound to Earth's soil. Now imagine the tallest mountain, Everest, rising nearly 9 kilometers above sea level. That's 9,000 meters. about 4,500 times taller than you. Standing at the bottom, you would look up at its snow-capped summit and see what feels like eternity above you. And yet, if Earth were the size of a smooth billiard ball, Everest would be just a tiny bump, less than the thickness of paint on the surface. Scale makes mountains majestic and microscopic all at once. From mountains, shift to the planet itself. Earth's diameter is about 12,142 kilometers. If you could shrink Earth down to the size of a globe in your classroom, you would be invisible on its surface, smaller than a dust speck. All your cities, oceans, roads, and lives would vanish in the thickness of varnish. The planet that feels so massive under your feet is, in truth, only a pebble in the larger solar landscape. This is where our imagination begins to stretch dangerously thin. We move from the scale of people, to trees, to mountains, to planets. And then suddenly, we are asked to jump millions of kilometers outward. Our brains are not designed to handle it naturally, so we invent tricks. Astronomers use analogies. Teachers use models. Writers tell stories. Each one is a ladder to climb from the human scale to the cosmic scale. One of the most famous thought experiments is the powers of 10. Imagine zooming out from a person sitting on a blanket in a park. At first, you see the grass, the trees, the city beyond. Keep zooming. At 10 kilometers out, you see the Earth's curvature. At 1,000, the whole Earth is a sphere, 10,000 kilometers more, and the Earth shrinks into a blue bead against the darkness of space. Keep going, and soon the moon enters the frame. Then the orbits of the planets. Then the sun. Then finally, the galaxy itself. Each step multiplies distance by 10, and with every leap, the familiar collapses into insignificance. But here's the trick. At every scale, something is home. At the scale of atoms, home is the cell. At the scale of people, home is the room. At the scale of planets, home is Earth. At the scale of galaxies, home is the Milky Way. Scale is not just about numbers, it's about belonging. And so, the human scale is not to be dismissed as small. It is the anchor from which all other measurements are made. Without your height, your stride, your lived sense of distance, the kilometer would mean nothing. The light year would be incomprehensible. Everything we measure out there begins with a comparison to what we know down here. Think of your daily world, walking to the store, driving 5 kilometers, flying across the continent. Even the longest flight you've ever taken, perhaps 12 hours, maybe 15, covers only a fraction of Earth's surface. Yet to you, it feels like forever. That's the tension between lived experience and cosmic truth. To you, a long trip feels enormous. To Earth, it is a minor scratch. To the galaxy, it is nothing at all. So why dwell on the human scale when our goal is to measure the universe? Because it teaches us humility and relatability. You are tiny, yes, but your tiny scale is the ruler we use to build bridges toward infinity. It is the stepping stone that lets your imagination take leaps without losing balance. Without it, the universe is just a blur of incomprehensible numbers. With it, the universe becomes a story you can walk into. Pause for a moment and look at your hand again. Trace the lines in your palm. Notice how the skin creases, how light shifts across the knuckles. That hand is your measuring stick, whether you realize it or not. In ancient times, people used cubits, the length of a forearm, to measure buildings. The body was the first ruler, and in a way it still is. The meter, after all, was originally based on the size of Earth itself, but it only made sense to us because it could be related back to the human stride, the human step. The human scale is not a limitation, it is a translation tool. The universe speaks in light years and parsecs, but we hear it in steps and breaths and moments. Without the human scale, the story of cosmic immensity cannot be told. So, as we stand at the threshold of greater distances, remember this. The human scale is not erased by the universe's immensity. It is framed by it, and in turn, frames it back. You are the ruler, the witness, and the interpreter. You are small, but your ability to imagine makes you vast. And that, perhaps, is the first secret of the universe's size. It is not only measured in kilometers or light years, but also in the stretch of the human mind, willing to leap from a single step to infinity. When you picture Earth floating in space, you might see the famous photographs from Apollo missions, the blue marble rising above the grey horizon of the moon. Our planet looks so fragile in those images, wrapped in swirling white clouds, oceans glittering like sapphires, continents stretching in greens and browns. This is where we live, the surface of a single world. But Earth, for all its richness, is only the first stepping stone on our way outward. To understand how big the universe is, we must first understand Earth's place within the larger cosmic arena. Let's start close. The Moon, our only natural satellite, has been circling Earth for billions of years. Its presence has guided tides, lit up dark nights, and inspired myths and stories across every culture in history. At first glance, it seems right there, hanging like a lantern in the sky. Children imagine reaching it with a ladder. Poets dream of walking across the gap. And in 1969, astronauts actually made the journey. But the numbers tell a different story. The Moon is about 384,000 kilometers away on average. That number is so big, it can blur into meaninglessness. So let's anchor it. Imagine shrinking Earth down to the size of a basketball. At that scale, the Moon would be the size of a tennis ball, placed about 7 meters away. That's roughly the length of a school bus. When you picture it that way, the distance suddenly feels larger, more real. Space is not just empty, it is spacious. And yet, despite this gap, the Earth-Moon system is tightly bound. The Moon always shows us the same face, its near side marked with dark maria that early astronomers thought were seas. Its far side remained hidden until spacecraft revealed a more cratered, rugged surface. The Moon is small compared to Earth, only about 1/4 its diameter, but its influence is immense. Without it, Earth's rotation would wobble chaotically, seasons might not be stable, and tides would not carve the coasts as they do. Our planet and its moon form a pair, a kind of dance in the darkness, reminding us that even small companions can matter enormously. But the moon is still just a neighbor. The true giant in our sky is the sun. At first glance, the sun and moon look about the same size. This coincidence of perspective, because the sun is 400 times larger than the moon, but also about 400 times farther away, is what makes eclipses possible. But make no mistake, the sun dwarfs everything in our system. It is 1.4 million kilometers in diameter, so vast that about 109 Earths could line up across its face. In terms of volume, over 1 million Earths could fit inside it. Think about that. The planet we call home, with its oceans and mountains and billions of lives, would be reduced to a droplet in the blazing ocean of the sun. And yet, the sun is only a medium-sized star, neither particularly large nor particularly small compared to the billions of others in the galaxy. Its distance, too, stretches the imagination. Light, moving at 300,000 kilometers per second, takes just over 8 minutes to travel from the sun to Earth. That means the sunlight warming your skin right now began its journey across space 8 minutes ago, bursting from the sun's surface after spending thousands of years clawing its way out from the star's dense interior. In other words, we don't see the sun as it is, we see it as it was 8 minutes ago. Even in our local neighborhood, space plays tricks with time. Beyond the sun, the planets spread out like beads on invisible strings. Mercury whips around in a tight orbit. Venus glows as Earth's bright twin. Mars lies a little farther, its red deserts cold and dusty. Then the gas giants take over. Jupiter, swollen and stormy. Saturn, crowned with rings that stretch like jeweled hoops. Uranus, tilted on its side. Neptune, deep blue and distant. Together, they form the family of worlds we call the solar system. But this family is not compact. It is stretched thin, with gulfs of empty space between siblings. For example, if the sun were reduced to the size of a soccer ball, Earth would be a tiny bead, just 2.5 centimeters across. orbiting about 26 meters away. Jupiter would be a grapefruit orbiting 140 meters away. Neptune, barely a marble, would be circling almost a kilometer from the soccer ball sun. Imagine standing in a field with the sun at the center and the planets scattered at these distances. The sheer emptiness between them would be staggering, and even then, we would not have reached the true edge of our solar system. Because beyond Neptune lies the Kuiper Belt, a ring of icy bodies and dwarf planets like Pluto. Beyond that, at distances so immense they are almost theoretical, lies the Oort cloud, a vast spherical shell of icy fragments that may extend halfway to the nearest stars. If Earth is our home and the sun is our hearth, then the Oort cloud is the far fence of our yard. To cross it would take tens of thousands of years, even at the speed of our fastest spacecraft. Already, our sense of scale is wobbling. The moon is far compared to us, yet near compared to the sun. The sun is gigantic compared to Earth, yet ordinary compared to other stars. The planets stretch across enormous gulfs, yet together they barely fill a pinprick in the map of the galaxy. This is the lesson of Earth's place in space. Every step outward redefines what big means. And yet there is comfort in this too. Earth is not lost in the immensity. It is positioned just right in what scientists call the habitable zone, the region around a star where liquid water can exist. Our moon steadies us. Our sun sustains us. The vacuum of space may feel hostile, but our cosmic neighborhood provides exactly the balance required for life to bloom. In the grand architecture of the universe, we occupy a small but golden niche. When you look at Earth from space, you do not see borders or cities. You see a single sphere, glowing softly against the darkness. All the noise of human quarrels, the rise and fall of empires, the rush of daily life, none of it is visible. Instead, you see one world, alive and unique. This perspective, often called the overview effect, has transformed astronauts who experienced it. They describe a sense of unity, of fragility, of awe. Earth is not big. Earth is not small. Earth is simply precious. And that, perhaps, is the real beginning of our journey outward. Because once you understand Earth's place, not as the center, not as the entirety, but as one world among countless, you are ready to stretch farther. From the moon to the sun, from the sun to the planets, from the planets to the edge of the solar system, each step enlarges the frame. But we must always glance back, remembering where we started. Because the farther we go, the more astonishing it becomes that such a small blue world could give birth to minds capable of imagining it all. When we leave Earth and think about the solar system as a whole, we enter a realm that stretches beyond anything the human body was ever meant to comprehend. Our planet and its moon, the familiar duo that anchors our nights and days, are just the inner pebble of an unimaginably vast arrangement of worlds, gas giants, icy fragments, and invisible boundaries. To understand how big the universe is, we first need to appreciate the sheer size of our own neighborhood, the solar system. Let's begin with a simple truth. Most of the solar system is not planets, moons, or comets. It is empty space. If you imagine the solar system as a grand ballroom, the planets are just a few dancers scattered around the floor, while the rest is open emptiness. The distances between those dancers are not measured in steps or meters, but in millions and billions of kilometers. Take Mars, for example. Our red neighbor lies about 225 million kilometers away from Earth on average. That's a distance so large that even when Mars is at its closest approach, it still takes light about 12 minutes to travel between the two planets. For comparison, radio signals to and from spacecraft traveling to Mars must always account for this delay, meaning engineers on Earth are always speaking into the past. That's how wide even a small step beyond Earth can feel. Now keep going outward. Beyond Mars lies the asteroid belt, a region often imagined as crowded with rocks colliding constantly. But in reality, the belt is mostly empty. Yes, there are countless asteroids, some hundreds of kilometers across, but they are separated by distances so great that a spaceship could sail through without ever noticing. Again, scale deceives us. Hollywood shows the belt as a gauntlet. Reality shows it as a lonely expanse with rare, scattered boulders drifting in silence. Beyond the belt lies Jupiter, the first of the true giants. Jupiter is more than 1,300 times the volume of Earth. Its stormy atmosphere hosts the Great Red Spot, a hurricane so huge that 3 Earths could fit inside it. Orbiting Jupiter are over 90 moons, ranging from small captured rocks to Ganymede, which is bigger than Mercury itself. The Jupiter system is almost like a miniature solar system of its own, with swirling moons and gravitational tides shaping their surfaces. One of those moons, Europa, may even harbor a hidden ocean beneath its icy shell, an ocean that has more water than all of Earth combined. Already within our own solar system, there are worlds as strange and promising as any science fiction story. Saturn comes next, adorned with its rings, which stretch hundreds of thousands of kilometers in diameter, yet are only a few dozen meters thick. Like Jupiter, Saturn is orbited by dozens of moons, including Titan, a world with rivers and lakes, not of water, but of liquid methane and ethane. Imagine standing on Titan's surface, watching a golden haze fill the sky, feeling the crunch of frozen hydrocarbons underfoot. This is still our solar system, still part of the backyard, yet the landscapes are alien beyond imagination. Farther out still, Uranus and Neptune reign in the icy reaches. Uranus tilts on its side, rolling like a spinning barrel as it orbits. Neptune's winds roar faster than the speed of sound, tearing through its cold blue atmosphere. Their distances are staggering. Neptune, the last major planet, orbits 30 times farther from the Sun than Earth does. That's 4.5 billion kilometers. At that distance, sunlight takes 4 hours to arrive. Imagine waiting 4 hours for a sunrise. Imagine living under a sun so faint that it looks more like a star than a burning disk. But even Neptune is not the end. Beyond its orbit lies the Kuiper Belt, a wide ring of icy bodies stretching billions of kilometers further. Here is Pluto, once called the 9th planet, now recognized as one of many dwarf planets sharing this outer ring. There's Eris, Haumea, Makemake, strange little worlds with orbits tilted and twisted, some with faint moons of their own. In 2015, the New Horizons spacecraft gave us our first close look at Pluto, revealing mountains of frozen nitrogen, plains of methane ice, and a heart-shaped glacier that seemed to whisper back across the void. Even here, at the edge, beauty thrives. And beyond even the Kuiper Belt lies the Oort cloud. This is no longer a tidy ring, but a vast spherical shell surrounding the Sun from every direction. It is made of icy fragments, leftovers from the solar system's birth, scattered so far away that they are almost lost to the galaxy itself. The Oort cloud may stretch out to 100,000 astronomical units. That's 100,000 times the distance between Earth and the Sun. To put it another way, if the distance from Earth to the Sun were the width of a coin, the Oort cloud would be several football fields away. This cloud is invisible to us. No telescope has ever seen it directly. We infer its existence because long-period comets, those icy travelers that streak into the inner solar system only once every few million years, must have started somewhere. Their orbits point back to this unseen frontier, a ghostly reservoir of frozen time capsules drifting in the deep dark. At this scale, even the fastest spacecraft humanity has ever built move like snails. Voyager 1, launched in 1977, has been flying for nearly half a century. It has crossed beyond the heliosphere, the bubble of space carved out by the Sun's solar wind, and is now in interstellar space. Yet by cosmic measures, it has barely left the driveway. To cross the Oort cloud, Voyager would need tens of thousands of years, and even then, the nearest star would still be far beyond. That's the staggering truth of the solar system. It is vast enough to humble us, yet still only the first ripple in the pond of the cosmos. From Earth to the Moon, from the Moon to the Sun, from the Sun to Neptune, and then onto the frozen shell of the Oort cloud. Every step reveals space that is larger, emptier and stranger than the last. And yet, within this immensity, we find intimacy. Each planet tells a story. Each moon harbors a mystery. The solar system is not just a vast emptiness. It is a tapestry woven with diverse worlds, each one a page in the grand book of the universe. By learning to see it not as an abstract set of numbers, but as a living neighborhood filled with landmarks and characters, we begin to train our imaginations for the greater leaps to come. Because beyond the Oort cloud lies something even more daunting: the stars. To reach them, we will need to stretch our scales once again, trading millions of kilometers for trillions, trading hours of sunlight for years of starlight. And as we do, we will discover that the solar system, immense as it feels, is just a small island in a far greater ocean. Beyond the frozen reaches of the Oort cloud, our sun's influence fades into the darkness. The solar wind, once a steady outflow of particles, weakens until the interstellar medium pushes back. This is the frontier where the domain of the sun ends and the kingdom of the stars begins. If the solar system is an island, then here we stand at the shoreline, gazing out across a sea of distant suns. The next question becomes, who are our nearest neighbors? The closest star system to Earth is the Alpha Centauri system, a trio of stars bound together by gravity. If our sun were reduced to a glowing lamp on a hill, Alpha Centauri would be another lamp across the plains, flickering faintly in the distance. That distance, however, is staggering. Alpha Centauri lies 4.24 light-years away. Light, the fastest thing in the universe, takes more than 4 years to cross that gulf. A spacecraft like Voyager 1, even if aimed perfectly toward it, would need tens of thousands of years to make the journey. But let's shrink this into something we can feel. Imagine the solar system compressed so that the sun is the size of a grain of sand. On that scale, Earth would orbit just a fraction of a millimeter away, barely visible. The Oort cloud, that vast icy shell, would be only a few centimeters out. Where then would Alpha Centauri be? Several meters away, another grain of sand resting on the floor. The nearest star is not across the room, it's across the field. Alpha Centauri is not just one star, but 3. The brightest is Alpha Centauri A, a sun much like ours, slightly larger and more luminous. Its companion, Alpha Centauri B, is a little smaller, glowing golden orange. The two orbit each other in a graceful cosmic dance, circling every 80 years. Then, orbiting farther out, is Proxima Centauri, a faint red dwarf star that is actually the closest of the 3 to us. Proxima Centauri is not impressive to look at. If you stood on a planet circling it, you would see a dim red glow in the sky instead of the brilliant disk we enjoy from our sun. But in 2016, astronomers discovered that Proxima hosts an Earth-sized planet, Proxima b, orbiting in its habitable zone. Suddenly, the nearest star system is not just an abstract point of light, it's a potential home. Though it may be bathed in flares and radiation, Proxima b remains a tantalizing target in the search for life beyond Earth. Think about this for a moment. The nearest star beyond our sun is unimaginably far. If you drove at highway speeds, 100 kilometers per hour, it would take more than 50 million years to reach Alpha Centauri. Yet in the vast scheme of the galaxy, Alpha Centauri is right next door. When we look up at the night sky, we see thousands of stars. The brightest, Sirius, shines twice as close as Alpha Centauri in terms of brightness, though not in distance. It is about 8 light-years away. Vega, Altair, Deneb, names woven into constellations, dot the sky within tens of light-years. Most of them are larger, hotter, or older than our sun. Some are red dwarfs, tiny embers that will outlive the universe itself. Others are blue giants, blazing so hot that they burn out in mere millions of years, living fast and dying young. And here is where perspective shifts again. The distances between stars are so immense that they redefine loneliness. Our solar system is a wide, empty bubble, but the space between stars is emptier still. If our sun were shrunk to the size of a coin, the nearest coin would be several football fields away, with nothing in between but darkness. This is the interstellar desert, and every star we see is another oasis, glowing faintly across the void. Astronomers call the region around us the local stellar neighborhood. It stretches about 30 light-years in every direction and contains a few hundred stars. Imagine living in a small town, scattered across a wide countryside. Each house is a star, each family of planets is a household. Some are close neighbors, just across the road. Others are so far you can barely see the light from their windows. That's our town in the galaxy, the local bubble of stars where we reside. Within this bubble, there are other intriguing systems. Barnard's star, a dim red dwarf, only 6 light-years away, is racing through space so quickly that it will one day replace Sirius as the brightest star in our skies. There's Wolf 359, another faint ember just under 8 light-years away, famous among science fiction fans. And then there are white dwarfs, stars that have burned through their fuel and collapsed into tiny, dense remnants. They are the ghostly echoes of once brilliant suns, reminders that stars, like people, have life cycles. But what makes this neighborhood special is not just its residents, it's its emptiness. Between every star lies light-years of space, and in that space floats dust, gas, and the faint whispers of cosmic rays. Humanity has only just dipped a toe into this interstellar ocean, with Voyager 1 and Voyager 2 drifting silently outward, their instruments aging, their signals weakening, carrying golden records with greetings in dozens of languages. They are our bottled messages tossed into the sea, hoping one day someone might find them. Think of how profound that is. Our entire history, all our cities, all our wars, all our art, has unfolded under the light of these nearby stars. For millennia, we looked up and saw them as eternal, fixed points of light. Only recently have we come to understand that they are suns in their own right, each with the potential for worlds, some perhaps even with oceans, mountains, and skies like ours. The night sky is not a backdrop, it is a crowd of neighbors, each impossibly distant, yet each real. And still, these neighbors are only the beginning. Beyond them, the stars multiply into millions, then billions, filling the disk of our galaxy. The step from the solar system to the nearest stars is the hardest, because it forces us to leave behind the comfort of the familiar and confront the true scale of interstellar space. Once we accept that even our nearest neighbors are light-years away, we are ready to look farther, to see the galaxy not as a scattering of points, but as a vast city of suns. For now, though, let's linger here in the neighborhood. Imagine floating beyond the edge of the Oort cloud, turning back to see the sun as a pale dot, no brighter than the other stars around it. You glance across the void, and there, faintly, shines Proxima Centauri. Not close enough to reach, not yet, but close enough to remind you that we are not alone in this darkness. Our solar system is not the only island. There are countless others, waiting, glittering, across the endless sea. If the space between stars feels immense, then the galaxy itself is something altogether different. Imagine leaving Earth, passing the Moon, Mars, Jupiter, and the edge of the solar system. You glide past the Oort cloud, leave behind Proxima Centauri and the other nearby stars, and keep going. After tens of thousands of years at Voyager's speed, you would still not be out of the neighborhood. The truth is, our sun and its planets are only one household among hundreds of billions, all bound together in the sprawling city of the Milky Way. The Milky Way is our home galaxy. When you step outside on a clear night, away from city lights, you may see it stretched across the sky like a faint milky band of light. Ancient people thought it was spilled milk, a river of stars, or even the path of the gods. Today we know it is the combined glow of billions of suns, too far away for the naked eye to see individually, woven together like threads of light. Let's try to imagine it. The Milky Way is a barred spiral galaxy. That means, instead of being a simple disk of stars, it has long spiral arms curling outward from a central bar-shaped core. If you looked at it from above, it would resemble a glowing pinwheel spinning slowly in space. The arms are where stars are born, in great clouds of gas and dust. The core, by contrast, is crowded and bright, with older stars packed tightly together. At the very center lies something more mysterious still. A supermassive black hole, known as Sagittarius A, millions of times the mass of the Sun. On the grand scale, the Milky Way is enormous. Its diameter is about 100,000 light-years across. That means if you shone a beam of light from one end to the other, it would take 100,000 years to complete the journey. To put it differently, imagine shrinking our entire solar system down so small that Pluto's orbit fits inside a coffee cup. On that scale, the Milky Way would be the size of North America. That is how tiny our place is within the galaxy. Our Sun is not at the center, nor at the edge, but somewhere in between. It resides in a quiet suburb known as the Orion Arm, a minor spiral arm between two of the major ones, the Sagittarius Arm and the Perseus Arm. Think of the Milky Way as a giant city. Its downtown is the galactic core, dense and bustling. The major arms are the busy avenues stretching outward, and the smaller arms, like Orion's, are the side streets where things are calmer. The Sun is about 27,000 light-years from the center, orbiting in this neighborhood, along with countless other stars. Yes, orbiting. Just as Earth circles the Sun itself moves around the galactic center. One complete orbit takes about 225 million years. The last time our solar system was in its current position in the galaxy, dinosaurs were just beginning to roam Earth. Since the Sun formed 4.6 billion years ago, it has completed only about 20 orbits of the Milky Way. We live not on a stationary stage, but in a system that is always moving through the galaxy, tracing slow, graceful paths among the stars. Within this disk, stars are not sprinkled evenly. They gather in clusters, associations, and sometimes in great nurseries where new suns are being born. The Orion Nebula, visible even with small telescopes, is one such nursery, a glowing cloud of gas where stars and planets are just beginning their lives. Elsewhere, old stars burn out and collapse, leaving behind white dwarfs, neutron stars, or even black holes. The galaxy is a place of constant birth, death, and renewal, each star part of a much larger cycle. And then there is the dark matter. Observations tell us the Milky Way contains far more mass than we can see. Stars spin around the galaxy at speeds that cannot be explained by visible matter alone. Something invisible, mysterious, and massive holds it all together. This is dark matter, a substance we cannot see or touch, but which makes up most of the galaxy's mass. Without it, the stars would fly apart like sparks from a fire. Dark matter is the unseen scaffolding on which the galaxy is built. From our vantage point, we cannot step outside and look back at the Milky Way. We are inside it, trapped in the middle of its glowing disk. The band of light we see in the sky is the view from within, a cross-section through billions of stars. To truly see the whole galaxy, we rely on observations of other galaxies and on careful measurements of star positions. Bit by bit, astronomers have pieced together a portrait. A spiral disk with 4 major arms, a central bulge, a halo of ancient stars, and a cocoon of dark matter holding it all in place. Even within this vastness, the Milky Way has structure beyond the arms and disk. Surrounding it is a halo populated by globular clusters, ancient, spherical collections of stars, some of the oldest in the universe. These clusters orbit far above and below the galactic plane, like lanterns hanging in the outskirts of a city. They remind us that the Milky Way has a long history, stretching back nearly to the dawn of the cosmos. The galaxy is not a static object. It lives, breathes, and changes over time. Stars drift, arms rotate, gas clouds collapse into new suns, and supernovae explode with brilliant violence, scattering heavy elements across the interstellar medium. Without those explosions, there would be no carbon, no oxygen, no iron, no ingredients for life. Every atom in our bodies was forged in the heart of a star and recycled through the galaxy, passed from one generation of suns to another. In this way, the Milky Way is not just our home, it is our ancestor. And the Milky Way is not alone. It is part of a small cluster of galaxies known as the Local Group, about 50 strong, dominated by two giants, the Milky Way and the Andromeda Galaxy. They are siblings in space, each with their own retinue of smaller satellite galaxies. In about 4 billion years, the Milky Way and Andromeda will collide, merging into a single larger galaxy. Stars will not smash into one another. There is too much space between them, but their orbits will be flung into new patterns. From Earth, if our descendants are still here, the sky will bloom with the sight of Andromeda swelling, twisting, and finally merging with our own galaxy into a magnificent elliptical shape. For now, though, our galaxy spins quietly in the cosmic night, its spiral arms sweeping gracefully, its stars rising and fading like sparks in a fire. When you look at the faint band of the Milky Way in the sky, remember what you are seeing. Not just light, but history. Billions of suns, billions of stories, billions of possibilities. And at the edge of one quiet arm, a small yellow star with a handful of planets orbits in silence, carrying with it beings who look up and wonder. The Milky Way is vast beyond comprehension, yet it is only one among 2 trillion galaxies in the observable universe. It is our home, but not the only home, To understand it is to take one step further into the grand puzzle of the cosmos. The next step, naturally, is to lift our eyes from our galaxy and look outward into the deep, intergalactic night. Imagine standing on the edge of our Milky Way, looking outward. Behind you lies 100,000 light years of swirling stars, nebula, and clusters. Ahead of you stretches the cosmic ocean, dark, silent, and filled with islands of light. These islands are galaxies, and they number in the trillions. If the Milky Way is our home city, then the universe is a boundless continent, filled with countless cities of every shape, size, and story. When astronomers first realized that galaxies existed beyond our own, it transformed our sense of scale. For centuries, the Milky Way was thought to be the entire universe. The stars we could see were assumed to be everything that existed, but in the 1920s, with the careful work of astronomers like Edwin Hubble, we learned the truth. Those faint smudges in the night sky were not nearby gas clouds, but entire galaxies, each one a universe of its own, containing billions of stars. The universe suddenly expanded in our minds. What we thought was everything became just one small corner in a cosmic archipelago, and the more we looked, the more we found. Today, with telescopes that can peer deep into time, we estimate there are around 2 trillion galaxies in the observable universe. Each galaxy is a library of suns, planets, black holes, nebulae, and mysteries we have yet to imagine. Galaxies come in many forms. Some are majestic spirals, like the Milky Way and Andromeda, their arms winding gracefully like pinwheels in the night. These spiral galaxies are fertile places for starbirth, their arms rich with gas and dust. Others are ellipticals, giant glowing orbs of stars, smooth and featureless, like cosmic balloons. Elliptical galaxies are often ancient, their star-forming days long behind them, filled instead with older, redder suns. Then there are irregular galaxies, the wild ones, their shapes twisted by collisions and gravity. They look like spilled ink, shattered fragments, or tangled knots of stars. The Magellanic Clouds, visible from the southern hemisphere, are irregular companions to our own galaxy. Some galaxies are tiny dwarfs with only a few million stars, while others, like IC 1101, stretch millions of light years across, containing perhaps 100 trillion stars. The diversity is staggering. If you could drift through the cosmos like a traveler, you would see galaxies of every kind, some neat, some chaotic, some glowing with new light, others fading into quiet. Each one is like a city with its own architecture, history, and fate. Galaxies are not static. They move, collide, and merge, drawn together by gravity. When 2 galaxies meet, they do not crash like solid objects. Instead, their stars pass mostly unharmed, while their shapes stretch and twist like taffy. Gravity pulls streams of stars into long tidal tails. New waves of star formation ignite, and black holes at their centers may flare brightly as they feed on surrounding gas. Over billions of years, such mergers build larger galaxies. Our own Milky Way is no exception. It has consumed smaller galaxies in the past, and traces of them still linger as streams of stars orbiting the outskirts. In the future, it will merge with Andromeda, creating a new giant galaxy. Collisions are not rare accidents, but part of the natural growth of cosmic structures. When you look at deep field images from the Hubble Space Telescope, filled with thousands of galaxies in a single tiny patch of sky, you are seeing not a static painting, but a dynamic story. Each galaxy is moving, interacting, evolving. The universe is not still. It is a grand dance that never stops. One of the strangest things about observing galaxies is that we never see them as they are now. Because light takes time to travel, distant galaxies are seen as they were millions or even billions of years ago. Looking outward is also looking backward in time. Some of the farthest galaxies we've detected are seen as they were only a few 100 million years after the Big Bang. Their light has traveled for more than 13 billion years to reach us. This means telescopes are not just tools for astronomy, but also for history. They let us watch the universe's earliest chapters, seeing galaxies just beginning to form, glowing faintly in the darkness of a young cosmos. In this way, galaxies are time machines. Each one tells a different story, depending on its distance. Nearby galaxies show us the present. Intermediate ones show us the Middle Ages of the universe. The farthest galaxies show us the dawn. Together, they let us piece together how the cosmos has grown from simple beginnings to the vast web we see today. If you could zoom out far enough beyond individual galaxies, you would see something even more extraordinary. Galaxies are not scattered randomly through space. They are arranged in a vast structure called the cosmic web. Like dewdrops on invisible threads, galaxies cluster along filaments of dark matter, separated by immense cosmic voids. These filaments form the largest structures in the universe, stretching across hundreds of millions of light years. They are rivers of galaxies flowing through the cosmos. The voids, by contrast, are vast empty regions where few galaxies exist. From a distance, the cosmic web looks like a three-dimensional spider web of light, an intricate network built on the hidden scaffolding of dark matter. This structure emerged from tiny fluctuations in the early universe, amplified by gravity over billions of years. Where matter was slightly denser, galaxies formed. Where it was thinner, voids grew. The cosmic web is a reminder that the universe, vast as it is, has an order and pattern, like a grand design woven in the fabric of space. It is natural to wonder, among these trillions of galaxies, how many hold planets like Earth? How many have life looking up at their own skies, asking the same questions we do? We cannot know yet, but the numbers are staggering. If each galaxy has billions of stars, and many of those stars have planets, then the number of possible habitable worlds is beyond counting. The universe could be teeming with life, or we could be rare, perhaps even unique. For now, we do not know. What we do know is that the raw ingredients of life, carbon, oxygen, nitrogen, water, are common across galaxies. The universe is built from the same chemistry everywhere. Every time we look at a galaxy, we are not just seeing stars, we are seeing potential homes. Some of those homes may already be occupied by beings who wonder about us, just as we wonder about them. The silence of the cosmos does not mean it is empty. It may mean we are still learning how to listen. When you think about galaxies, it is easy to feel small. Our solar system is a tiny dot in the Milky Way, which is itself just one among trillions. Yet there is another way to look at it. We are not separate from this immensity. We are made of it. The atoms in our bodies were forged in ancient stars, scattered across the galaxy, and gathered here by chance. We are threads in the cosmic web, part of the same story as the galaxies we admire. The light from distant galaxies travels billions of years to reach our eyes, and yet, here we are, able to see it, to think about it, to tell its story. That is not small at all. It is a sign that the universe, vast though it is has given rise to beings capable of wonder. So when you gaze at a photograph of galaxies, spirals, ellipticals, irregulars, remember what you are looking at. These are not distant decorations. They are families of stars, cosmic cities, living histories. They are reminders that the universe is larger than our fears, older than our lives, and richer than our imagination. And the story does not end with galaxies. Beyond them lies something even greater, the large-scale history of the universe itself, from its fiery beginning to its mysterious fate. To step further outward is to step into the story of time itself. Close your eyes and imagine rewinding the universe. Every star, every galaxy, every planet, every particle of dust, moving backward in time. Galaxies drift together, stars unravel, planets dissolve. All the matter spreads thinner and thinner across the past. Keep going, billions of years into rewind, until you reach a point where everything that exists was once compressed into a space smaller than a single atom. That moment is where our story begins. The Big Bang. The Big Bang was not an explosion in space. It was an expansion of space itself. In the very first fraction of a second, less than a heartbeat, less than a blink, the universe grew from unimaginably small to unimaginably vast. Time itself began. Space itself began. The very fabric of reality unfolded. Physicists believe that in this tiny sliver of time, the universe went through a phase called cosmic inflation. Imagine blowing up a balloon, not slowly, but so quickly that in less than a trillionth of a second, it has expanded to cosmic scales. That is what inflation did to the early universe. It smoothed out the wrinkles, stretched out the energy, and set the stage for everything that would follow. When the inflationary growth slowed, the universe was a hot, dense soup of energy and particles. Temperatures were so high that matter as we know it could not exist. Instead, the cosmos was filled with a plasma, a glowing fog of particles and light, constantly colliding, unable to settle. In those first seconds, the simplest ingredients of the universe formed. Protons and neutrons came together, the seeds of atomic nuclei. Within minutes, hydrogen and helium were born, along with traces of lithium. These were the first elements, forged not in stars, but in the Big Bang itself. The heavier elements, carbon, oxygen, iron, the building blocks of life, would come much later, inside stars. But hydrogen and helium were enough to begin. They filled the young universe like the foundation of a cosmic recipe, waiting for time and gravity to do their work. For hundreds of thousands of years, the universe was opaque. Light could not travel far without being scattered by particles. Imagine standing inside a thick cloud. You would see only brightness all around, no clear shapes. That was the early universe, glowing but hidden. Then, about 380,000 years after the Big Bang, a quiet miracle happened. The universe cooled just enough for electrons to settle into orbits around nuclei, forming the first true atoms. With electrons now attached, light no longer scattered so easily. Suddenly, the universe became transparent. The fog lifted. Photons, particles of light, were free to travel through space. We can still see that ancient light today. It is called the cosmic microwave background, CMB, the faint afterglow of the Big Bang. It fills the universe in every direction, a cool whisper of radiation that carries the fingerprint of the first atoms forming. Every microwave oven, every radio antenna could in theory pick up this signal from the dawn of time. When scientists mapped the CMB with satellites like COBE, WMAP and Planck, they found something astonishing. It is almost perfectly smooth, the same in every direction, but not entirely. Tiny ripples, just fractions of a degree warmer or cooler, show where matter was slightly denser. Those ripples are the seeds of galaxies. From those tiny differences, gravity would slowly sculpt the cosmic web. For millions of years after the fog lifted, the universe was dark. They build atmospheres of light for planets, guide travelers with their glow, and maintain the balance of galaxies. It is in these middle years that stars nurture planetary systems. Around the Sun, planets formed from the leftover dust and gas of its birth. Earth settled into orbit, bathed in sunlight, becoming a cradle for life. Without the long, stable warmth of a star, life as we know it would not have the chance to grow. But stars cannot burn forever. As hydrogen in the core runs low, the balance between gravity and fusion begins to shift. The star changes. In medium-sized stars like the Sun, when hydrogen is depleted, the core contracts under gravity while the outer layers expand. The star swells enormously, becoming a red giant. Imagine the Sun swelling until it reaches beyond Earth's orbit, swallowing Mercury and Venus, and possibly Earth as well. Its surface would cool, glowing red, but its size would be vast. Inside, fusion shifts to new fuels. Helium fuses into carbon and oxygen, creating heavier elements. The star struggles to keep balance, its life nearing its end. For massive stars, the story is even more dramatic. When they run out of hydrogen, they burn through helium, then carbon, then neon, oxygen, and silicon, stacking elements like layers of an onion. Each stage burns faster, until finally, the core is iron, a dead end. Fusion cannot continue with iron. The star's fate is sealed. How a star dies depends on its size. Small stars, like red dwarfs, fade quietly. They burn slowly until, after trillions of years, they simply cool into dark, cold remnants. No fireworks, just a long, gentle fading. Medium stars, like our Sun, end with beauty. After swelling into red giants, they shed their outer layers into space, forming glowing shells called planetary nebulae. These nebulae shine in delicate colors, blue, green, red, as if the star is painting the sky with its farewell. At the center, the core remains as a white dwarf, a small, dense ember of a star, glowing with leftover heat. Over billions of years, it too will fade into darkness. Massive stars go out with violence. When their cores fill with iron, fusion halts, and gravity wins. The star collapses inward, then rebounds in a titanic explosion, a supernova. For a brief moment, the star can outshine an entire galaxy. The blast scatters heavy elements into space: gold, silver, uranium, all the rarest materials of the cosmos. These explosions are the reason planets and people exist. Every atom of iron in your blood, every atom of calcium in your bones was forged in a star's death. After the explosion, the core may become a neutron star, so dense that a teaspoon of its matter would weigh billions of tons. Or, if the star was truly massive, collapse continues into a black hole, a region where gravity is so strong that not even light can escape. Stars do not simply die and vanish. They leave behind gifts. The gas they release enriches galaxies with heavy elements, seeding future generations of stars and planets. The carbon, oxygen, and nitrogen scattered by old stars become part of new worlds. In this way, the life cycle of stars is a cosmic recycling system. One generation passes, another arises. Galaxies are gardens, stars the gardeners, and their fruits are worlds capable of life. Astronomer Carl Sagan once said, "We are made of star stuff." This is not poetry, it is literal truth. The atoms in your body, the iron in your blood, the calcium in your teeth, the oxygen you breathe, all were created in stars that lived and died billions of years ago. To know the life cycle of stars is to know your own origin. Let's trace this cycle as if it were a single life. Birth. In dark clouds, a protostar gathers. Fusion begins. Youth. The star settles into stability, glowing steadily. Adulthood. Billions of years pass as hydrogen burns in the core. Old age. The star swells, fusing heavier elements, becoming unstable. death. Depending on size, the star fades gently as a white dwarf or dies violently as a supernova. Legacy. Its ashes enrich the universe, seeding new stars and planets. This cycle has repeated countless times across billions of years. Each star is a chapter in the universe's story, each death the prelude to new life. For as long as humans have looked at the sky, stars have guided us. They mark seasons, inspire myths, and spark wonder. Ancient navigators crossed oceans by their light. Farmers planted crops by their rising and setting. Poets compared them to diamonds, fires, or eyes of gods. Today, we understand stars scientifically, yet they still touch us with awe. A sunset, the sparkle of Orion's belt, the shimmering Milky Way. These are not just scientific objects, but emotional experiences. They remind us of our smallness and our belonging in something vast. When you look at a star tonight, you are seeing both light and history. That glow may have traveled for thousands, even millions of years to reach your eyes. You are looking back in time, witnessing a star as it once was. The story of stars will not end soon. Red dwarfs, the most common stars in the universe, will burn for trillions of years, long after our sun and all the bright stars you know have faded. The universe will one day belong to them, tiny but enduring, the slow embers of cosmic fire. Eventually, even they will go dark. The future holds a quiet cosmos, with black dwarfs, neutron stars, and black holes wandering in the cold. Yet even in that distant time, the memory of stars will live on, in the elements they created, in the worlds they built, in the beings who once gazed at them with wonder. The life cycle of stars is more than a scientific process. It is a story of transformation, of creation and renewal. Stars are born from darkness, shine with brilliance, and return to the dark. But in dying, they create the possibility of life. When you breathe air made in stars. When you drink water made of hydrogen from the Big Bang. When you think, the neurons in your brain fire with atoms once inside a star's heart. You are the universe reflecting on itself, a star's legacy brought to consciousness. The next time you see the night sky, remember, every star is a story in progress. Some are beginning, some are ending, but all are connected in a grand cycle that spans billions of years. And you, sitting here now, are part of that cycle. You are not separate from the stars. You are their continuation. The stars live, and so do you. Imagine for a moment that you are standing on a quiet hill at night, gazing up at the Milky Way as it stretches like a misty ribbon across the sky. Every glimmer you see is a star in our galaxy. But just beyond that faint river of light lies a secret that dwarfs everything we've spoken about so far. Because out there, looming like a great neighbor just across the cosmic fence, is another giant, Andromeda. It's not a faint, distant mystery to astronomers, but a real, massive, spiraling companion to our galaxy. If the Milky Way were a great city, Andromeda would be the sprawling metropolis on the horizon, visible in the distance but destined one day to merge with us. Andromeda, also known as Messier 31 or M31, is the nearest spiral galaxy to the Milky Way, sitting about 2.5 million light-years away. That distance is almost impossible to wrap your head around. Remember, a single light-year is the distance light travels in 1 year, about 9.46 trillion kilometers. So if you want to picture Andromeda's distance, imagine stacking trillions upon trillions of kilometers together and then multiplying by 2.5 million. Yet, despite being so far away, Andromeda is actually visible to the naked eye under dark skies. If you've ever seen a faint smudge of light near the constellation Andromeda, stretching like a tiny thumbprint on the sky, you've seen an entire galaxy, hundreds of billions of stars, wrapped into a spiral form, glowing from unimaginable distances. The sheer size of Andromeda makes our own Milky Way look modest. For years, astronomers debated which of the two was bigger. The Milky Way is roughly 100,000 light-years across, maybe a bit more. Andromeda, however, stretches over 220,000 light-years from one end to the other, more than twice as wide. It contains an estimated trillion stars, compared to the Milky Way's 200 to 400 billion. Imagine walking into a grand library where each star is a book. In the Milky Way, you'd be surrounded by hundreds of billions of volumes, already more than a lifetime could ever comprehend. But step into Andromeda's halls, and the shelves expand beyond sight, stacked with 1 trillion shining stories. And Andromeda is not just enormous, it's active. Its spiral arms swirl with dust and gas, creating pockets where new stars are born. Astronomers have spotted hot, massive stars glowing brightly within it, as well as ancient star clusters that have survived for billions of years. Its central bulge, the dense area of stars at the galaxy's heart, contains a supermassive black hole, much like the Milky Way's Sagittarius A. This black hole, weighing perhaps 100 million times the mass of our Sun, dominates the inner core. The galaxy itself rotates majestically, arms sweeping like the blades of a windmill, a cosmic dance that has been unfolding for eons. Now here is where things become even more fascinating. Andromeda is on a collision course with the Milky Way. That might sound dramatic, and in a way it is, but don't worry. The crash won't happen tomorrow, or next year, or even in the next million years. The predicted timeline places the merger about 4 billion years from now. Still, in cosmic terms, that's relatively soon. The Andromeda galaxy is moving toward us at a speed of about 110 kilometers per second. That's over 240,000 miles per hour. Every second that passes, it is slightly closer, creeping across the void that separates us. What does a galactic collision actually look like? It's not quite as catastrophic as the word collision suggests. Remember, galaxies are mostly empty space. Stars are scattered so far apart that when two galaxies overlap, most stars pass right by each other, never colliding directly. Instead, what happens is a slow, graceful intermingling. The gravitational fields of the galaxies tug and pull, stretching out long streams of stars, warping spiral arms into tidal tails, flinging some stars into intergalactic space. Gas clouds collide and compress, sparking waves of new star formation. For a while, the Milky Way and Andromeda will look like two lovers locked in a long embrace, swirling together in chaotic beauty. Over billions of years, the two galaxies will gradually fuse into one massive elliptical galaxy, sometimes nicknamed Milkomeda by astronomers. It will no longer be a neat spiral shape like we know today, but a puffed-up, rounded galaxy glowing with combined starlight. Imagine the night sky of Earth's far future. If humanity, or whatever descendants we might leave behind, still exists, they will look up to see not a misty band of the Milky Way, but a sky blazing with streams of stars from two merging galaxies. And when Andromeda grows close enough, it will dominate the heavens. Instead of a tiny smudge, it will stretch across the entire sky, glowing with billions of suns. The view will be breathtaking, like fireworks on a cosmic scale. To understand this process, astronomers have run computer simulations, feeding in data about the motion, mass, and gravitational pull of both galaxies. These simulations produce stunning visualizations of the future. First, Andromeda grows larger and brighter. Then, as the galaxies approach, long tails of stars stretch outward. Eventually, after several passes, the two galaxies sink into one another and merge into a single colossal structure. What's most astonishing is how serene the process looks. It isn't a sudden crash, but a long, drawn-out dance, lasting billions of years. This raises another question. What will happen to our Sun and our solar system during this galactic merger? While it's unlikely that our Sun will collide with another star, its orbit within the galaxy could be altered by the gravitational chaos. We might be flung into a new part of the galaxy, perhaps closer to the core or pushed toward the edges. Earth and its siblings could find themselves under a completely new night sky, surrounded by different constellations. It's an unsettling thought, but also thrilling. our descendants may live under skies unrecognizable to us, painted with the fires of new stars born in the collision. Andromeda also helps us understand that galaxies are not static, isolated islands. They are part of a dynamic, interconnected universe, constantly moving, pulling, and shaping each other. The fact that Andromeda and the Milky Way are destined to merge shows us that galaxies evolve, change, and even die in a way. Spirals can become ellipticals, stars are created and destroyed, and even the largest structures in the cosmos are temporary arrangements. On the timescale of billions of years, change is the only constant. Now imagine zooming outward a little more. If you could view the Milky Way and Andromeda from above, you'd see them as two grand spirals drifting toward each other, surrounded by smaller companion galaxies like satellites. Already, the gravitational pull of Andromeda affects some of these companions, just as the Milky Way shepherds its own dwarf galaxies. This isn't just a two-body dance, it's a family reunion of entire galactic systems, all tangled in gravity's invisible web. The local group, our neighborhood of galaxies, is bound by this same interplay, and the merger of its two giants will reshape the balance of power forever. There's also something deeply humbling about knowing that even galaxies, these titanic structures of unimaginable size, are not permanent. They collide, they merge, they transform. Our place in the Milky Way is temporary, just like everything else, and yet, in the midst of all that change, there is beauty. The beauty of watching cosmic structures grow and evolve. The beauty of knowing that the universe itself is alive with movement and transformation. So when you look up at the faint smudge of Andromeda in the night sky, remember this: you are not just looking at a distant galaxy. You are looking at our future. You are seeing the partner that will one day join with the Milky Way to create a new galaxy. You are witnessing not just history, but destiny. The universe is vast, and sometimes it feels cold and impersonal, but in moments like this, it feels almost like a story. A story in which we, tiny humans on a small blue planet, are connected to events billions of years in the making. The Andromeda Giant is more than a distant smudge. It is a reminder of cosmic scale, of how even something as massive as a galaxy is part of a larger journey. It is both our neighbor and our future, and its immense presence helps us understand just how big and how dynamic the universe really is. Let us drift further outward from our spiral home and its looming neighbor Andromeda, until we see not just galaxies, but the vast communities they form. Because galaxies are not solitary wanderers, scattered like pebbles across a beach. They live in neighborhoods, bound together in groups, clusters and superclusters, woven into an immense cosmic web that stretches across the entire universe. If galaxies are like cities, then these groups are the nations and continents of the cosmos, joined by invisible filaments of dark matter and gas. Our own Milky Way belongs to what is called the local group, a collection of about 80 or so galaxies tied together by gravity. The local group is modest compared to some of the larger cosmic gatherings. At its heart are two giants, the Milky Way and Andromeda, each with their retinue of smaller dwarf galaxies, like moons circling planets. The Triangulum Galaxy, or M33, is another fairly large member, though still far smaller than its two bigger siblings. The rest are dwarfs, tiny collections of a few million or billion stars, many of them faint and irregular, almost ghost-like in their appearance. From our vantage point, these small galaxies seem unremarkable, but in fact, they play an important role in galactic evolution. Dwarfs often serve as building blocks. Larger galaxies grow by swallowing smaller ones, tearing them apart with tidal forces and incorporating their stars and gas. Astronomers call this galactic cannibalism, and it has been happening since the universe began. The Milky Way itself shows scars of such feasts, faint streams of stars, remnants of galaxies that were long ago pulled in and devoured. Even now, the Milky Way is in the process of consuming the Sagittarius dwarf galaxy, its stars stretched into long ribbons across our sky. The local group as a whole stretches about 10 million light-years across. That's vast beyond imagining, yet tiny compared to what lies beyond. Our group does not float in isolation. It is part of an even grander arrangement called the Virgo supercluster, a sprawling expanse containing thousands of galaxies organized into clusters. Imagine flying across this region. You would pass through knots of galaxies grouped tightly together, like glowing islands in a cosmic sea. Between them are filaments of matter, dark rivers that connect these islands into one vast structure. The Virgo cluster itself, located about 55 million light-years away, dominates our supercluster. It contains more than 1,000 galaxies, from giant ellipticals to graceful spirals, and is so massive that its gravity influences even the local group. You could say the Virgo cluster is like the capital city of this supercluster, and we, far out on the suburbs, feel its pull across the void. And here's where the scale expands again. In recent years, astronomers have mapped the universe in ways that reveal patterns on almost inconceivable scales. They discovered that the Virgo supercluster is not the true boundary of our region at all, but just one part of something much larger, a structure they named Laniakea, meaning immense heaven in Hawaiian. This supercluster of superclusters spans 500 million light-years and contains over 100,000 galaxies. To put that in perspective, if the Milky Way were a single grain of sand, then Laniakea would be a continent of glittering beaches stretching out in every direction. Laniakea is shaped not as a random blob, but as part of a cosmic web, the largest structure in the universe. Computer simulations and galaxy surveys have revealed this web as a pattern of filaments and voids. Filaments are long strands of galaxies, drawn together by gravity and dark matter. They crisscross space like threads in a colossal net. Between these filaments lie voids, enormous regions nearly empty of galaxies, sometimes hundreds of millions of light-years across. Imagine walking through a city at night where most streets are bustling with lights, but then turning into a vast, dark field where no houses stand. That's what these voids are, lonely regions of space where matter is sparse and silence reigns. The idea of the cosmic web is one of the most profound discoveries of modern astronomy. It shows us that the universe is not random chaos, but structured on the grandest of scales. From stars forming in nebulae to galaxies clustering into filaments, patterns repeat themselves. The universe is self-organizing, shaped by gravity, dark matter, and dark energy into something that resembles a living organism, with filaments like arteries carrying the flow of galaxies across the cosmos. Now, let's slow down and picture one of these galaxy clusters in detail. Imagine floating on the edge of the Coma cluster, one of the richest galaxy clusters known, 320 million light-years from Earth. From your vantage point, thousands of galaxies crowd the sky, glowing like lanterns packed tightly together. Many are ellipticals, giant balls of stars formed from countless mergers. The hot gas between them shines in X-rays, filling the space with a diffuse glow. Dark matter, invisible but dominant, holds the cluster together like glue. To look upon such a cluster is to realize how small even something like the Milky Way really is. A single galaxy among thousands, each with its own stars, planets, and perhaps life. Clusters and superclusters also tell us something important about the fate of the universe. Galaxies fall together under gravity, but they are also being pulled apart by another force, dark energy. This mysterious energy permeates space and drives the accelerated expansion of the universe. It means that while local structures like the local group remain bound, distant galaxies and clusters are drifting ever further apart. Over billions of years, the cosmic web itself will stretch, its filaments thinning as galaxies recede from each other. One day, far in the future, galaxies beyond our local supercluster will disappear from view entirely, carried away faster than light can bring their image to us. Our descendants will live in a universe that feels emptier, isolated within their own cosmic island. But for now, we live in a universe alive with structure. Superclusters like Laniakea remind us of the vast networks that bind us together. They also remind us that we are part of something larger, much larger, than even a galaxy collision. The story of the cosmos is not just stars and planets, but entire galaxies flowing like rivers across space, guided by forces we are only beginning to understand. Let's also pause for a moment and think about what it means that human beings, fragile creatures on a small rocky planet, have mapped this cosmic web. With our telescopes and satellites, we've traced the outlines of structures spanning hundreds of millions of light years. We've discovered that our galaxy is not alone, nor even dominant, but a tiny part of a web so vast it stretches beyond our imagination. This knowledge is humbling, but also inspiring. It means that no matter how small we may feel, we are capable of reaching outward, of understanding, of connecting the dots in the greatest puzzle of all. Picture again the local group, with the Milky Way and Andromeda slowly spiraling toward each other. Now zoom outward to the Virgo cluster, a metropolis of galaxies. Zoom further still to Laniakea, with its rivers of stars flowing across space. And finally, step back to see the entire cosmic web, glowing like a vast neural network, filaments branching out, voids stretching wide, the whole thing alive with motion. It is beautiful, it is immense, and it is the universe we belong to. The galaxies beyond the Milky Way are not just distant lights. They are part of a vast cosmic architecture, and their story is our story too. We are citizens not only of Earth or of the Milky Way, but of the local group, of the Virgo supercluster, of Laniakea, and of the universe itself. Every time you look up at the night sky, you are seeing only a tiny fragment of this story, but within that fragment lies the key to understanding it all. There are also ideas involving sterile neutrinos, relatives of the known neutrinos, but even more elusive. Experiments deep underground, shielded from cosmic rays, are designed to catch a rare interaction between dark matter and ordinary particles. Huge detectors filled with liquid xenon or other materials wait in silence, hoping to see a single flash of light when a dark matter particle passes through. So far, no clear detection has been made. Dark matter remains hidden, its nature a riddle. Still, its effects are everywhere. Without dark matter, galaxies would not have formed. After the Big Bang, the universe was nearly smooth, but dark matter, being invisible and unbothered by light, began clumping early. These clumps acted like seeds, drawing in normal matter to form stars and galaxies. The cosmic web itself, those great filaments of galaxies stretching across billions of light years, is shaped by dark matter. It is not just a background presence, it is the architect of structure. If dark matter is the cosmic scaffolding, then dark energy is something stranger still, the force that tears scaffolding apart. In the late 1990s, two teams of astronomers studying distant supernovae made a shocking discovery. They expected the universe's expansion to be slowing down under gravity. Instead, they found it was speeding up. Some mysterious energy, spread throughout space itself, was driving this acceleration. They called it dark energy. To imagine dark energy, think of space as a balloon. Galaxies are like dots on the balloon's surface. As the balloon expands, the dots move apart. But instead of slowing, the expansion accelerates, as if someone keeps blowing harder and harder into the balloon. Dark energy is that push, an unknown pressure that grows as the universe expands. Today, dark energy is thought to make up about 70% of the universe's total energy. Its effect is profound. It dictates the universe's fate. Left unchecked, dark energy will continue to drive galaxies further apart until only local groups remain bound together. In the far future, the universe will be dark and lonely, with each cluster isolated, surrounded by ever-growing voids. What is dark energy? There are several theories. One is that it is the cosmological constant, an idea first proposed by Einstein. It suggests that empty space itself has energy, a kind of vacuum energy that exerts a repulsive force. Another idea is that dark energy is a quintessence field. a dynamic energy that changes over time, like a ghostly fluid permeating the cosmos. Some physicists wonder if our understanding of gravity itself needs revision, and dark energy is not a separate thing, but a sign that Einstein's theory is incomplete. Whatever it is, dark energy is the dominant driver of the cosmos. Its discovery was so revolutionary that it earned the 2011 Nobel Prize in Physics. And yet, like dark matter, it remains unsolved. It is as if we can see the shadow of a creature moving behind the curtain, but cannot glimpse its true form. Let us take stock. About 70% of the universe is dark energy, about 25% is dark matter, and only about 5% is ordinary matter. That means nearly everything we experience is the exception, not the rule. The bright stars, the glowing galaxies, the warm light of our sun, all are built from a cosmic minority. We live in a dark universe. This realization is humbling. It means that for all our science, most of reality is still hidden. And yet, in another sense, it is wondrous. We are creatures of that small 5%, and somehow we have managed to uncover the existence of the other 95%. We have inferred their presence not by seeing them directly, but by watching their effects. Galaxies spinning too fast, supernovae too dim, space itself stretching quicker and quicker. It is a reminder that knowledge is not always about seeing, but about understanding patterns, connecting dots, and trusting the story written in the stars. Dark matter and dark energy also tell us about the universe's fate. If dark energy continues to dominate, then galaxies will drift apart faster and faster. Stars will burn out, galaxies will dim, and the universe will grow colder and darker, a future sometimes called the heat death. In this vision, time stretches into infinity, with only black holes and fading embers remaining. Some theories, however, suggest more dramatic endings. If dark energy grows stronger over time, it could lead to the Big Rip, where galaxies, stars, planets, and even atoms are torn apart by the expansion. On the other hand, if dark energy fades or reverses, gravity could take over, pulling everything back into a big crunch. Or perhaps the universe will cycle endlessly, expanding and collapsing in a cosmic heartbeat. We do not yet know which path is true, but every observation, every measurement of dark matter and dark energy brings us closer to the answer. Pause and think of this for a moment. On a small blue planet orbiting an ordinary star, a species of curious beings has uncovered the existence of invisible matter and mysterious energy shaping the cosmos. With telescopes and equations, we've pulled back the curtain on a universe far stranger than our ancestors could have imagined. And yet, this strangeness is not frightening. It is beautiful. It shows us that reality is deeper than appearances. Just as an atom contains hidden depths, so does the universe. And by seeking those depths, we connect with something larger than ourselves. The story of dark matter and dark energy is not finished. It is a frontier, one of the greatest quests in science. Perhaps one day, children born centuries from now will look back at us as the generation that first glimpsed the shadows, the pioneers who dared to ask, what is the universe really made of? Dark matter, the hidden scaffolding. Dark energy, the invisible engine. Together, they shape the cosmos. Together, they remind us that the universe is vast, mysterious, and alive with secrets waiting to be uncovered. Imagine lifting your gaze away from single galaxies and even beyond clusters. Up until now, our journey has taken us from the familiar scale of Earth to the swirling majesty of the Milky Way, out across the local group, and then further still into the vast supercluster of Laniakea. But there comes a point where even superclusters, enormous as they are only fragments of something much grander. When astronomers mapped the positions of galaxies across billions of light years, they discovered a striking truth. The universe is not randomly scattered like dust, but instead arranged in enormous patterns, delicate, sprawling networks of filaments, knots, and walls that weave together a structure unlike anything else we know. This is the cosmic web, the largest arrangement of matter ever observed, and one of the most beautiful. The first hint of this structure came in the late 20th century, when surveys such as the CFA Redshift survey charted galaxy positions across the sky. Astronomers expected to see galaxies evenly sprinkled, like raisins in a vast bread dough. Instead, they found tendrils and sheets, dense lines of galaxies stretching in arcs and threads, separated by yawning voids. It was as though the universe itself had woven a net, each glowing galaxy like a pearl on its strand. Later, with the Sloan Digital Sky Survey and other deep all-sky catalogues, the picture became clearer. Galaxies congregate along immense walls, and these walls connect to other walls through thin bridges of galaxies and clusters, forming filaments that span hundreds of millions of light years. In between are cavities, the voids, nearly empty of galaxies. Together, these filaments and voids give the cosmos a foamy appearance on scales so large that it staggers imagination. Let's take a walk through this web, or at least try to picture it. Start close to home. Our Milky Way, along with Andromeda and other members of the local group, sits inside a filament that belongs to Laniakea. This filament stretches far beyond, connecting us to other dense regions of galaxies. Travel outward, and you'd see our filament merge with larger ones, linking together into grand arcs. If we could somehow step back, farther than is physically possible, but useful to imagine, we'd see the universe as a ghostly mesh, glowing in patches where galaxies are most concentrated and dim elsewhere. These filaments span sizes that dwarf even superclusters. Some stretch for over 500 million light-years, forming what astronomers call Great Walls. One famous example is the Sloan Great Wall, discovered in 2003. At over 1.3 billion light-years in length, it's one of the largest known structures in the observable universe. Imagine walking across such a structure. Even if you traveled at the speed of light, it would take you over 1 billion years to cross from end to end. And yet, despite its immensity, the Sloan Great Wall is just one thread in the web. Other gigantic formations include the Hercules Corona Borealis Great Wall, discovered in 2013, which may be over 10 billion light-years across. At that size, it rivals the limits of what cosmology predicts can even exist. Some scientists debate whether these walls are single connected objects or simply chance alignments of filaments, but even so, the fact that we observe such immense structures tells us the universe's fabric is astonishingly intricate. So, why does matter arrange itself this way? The answer lies in the subtle imprints of the early universe. When the cosmos was young, only a few 100,000 years old, it was a hot soup of particles and radiation. Tiny fluctuations, slightly denser patches here, slightly emptier ones there, were frozen into this plasma. Over billions of years, gravity pulled more material into the denser regions, amplifying them, while emptier zones became the vast voids we see now. This process, simulated on supercomputers, produces networks that look uncannily like the real cosmic web, filaments, knots, and voids, stretching endlessly in all directions. In other words, today's immense cosmic architecture was seeded in the faint ripples of the Big Bang itself. Let's slow down for a moment and imagine drifting along a filament. Ahead, the sky is bright with galaxies, spirals, ellipticals, dwarfs, all shining together, drawn by the shared gravity of their filament. It would feel like traveling down a cosmic highway, galaxies zipping past like streetlights on either side. Then suddenly, you'd reach a crossing point, a dense knot, glowing with clusters upon clusters, perhaps home to thousands of galaxies bound together. Past the knot, the road continues, stretching out like a bridge across unimaginable emptiness. And then, suddenly, the bridge stops. Ahead is only void, a region so empty it may contain just a handful of galaxies scattered across hundreds of millions of light years. The contrast between the crowded filaments and the lonely voids is stark, like passing from a bustling city into a desert that seems to have no end. There's a poetic beauty to this arrangement. On smaller scales, stars cluster into galaxies, and galaxies gather into clusters. But on the grandest scales, clusters themselves link into a web that stretches across the observable universe. Nature has created a pattern that echoes across every level. Structure arising from simplicity, order growing from initial randomness. And it's not only beautiful, it's crucial. The filaments guide the growth of galaxies, channeling matter into certain paths, influencing where stars form and where black holes grow. Even the way dark matter, the invisible backbone of the cosmos, arranges itself mirrors this same web. In fact, the cosmic web is sometimes described as the skeleton of the universe, with galaxies and clusters forming the flesh draped upon it. But let's not lose sight of the scale here. When we say a filament is hundreds of millions of light years long, we're talking about scales that dwarf anything familiar. If you were to shrink the Milky Way down to the size of a single grain of sand, then a typical cosmic filament might be as long as the distance between continents. And yet, within that strand, every grain is itself a galaxy, with billions of stars. The numbers stack upon numbers, the immensity compounding until human imagination falters. Scientists continue to map these structures using both ground-based telescopes and space observatories. Projects like the Dark Energy Survey and Euclid mission aim to chart ever larger volumes of the cosmos, tracing the filaments more clearly and probing how they evolve over time. By studying the cosmic web, astronomers hope to understand not just where galaxies are, but why they are there, and what that tells us about the universe's history, composition, and fate. For all its grandeur, though, the web also reminds us of fragility. If the early universe's fluctuations had been slightly different, the filaments might not have formed as we see them. Galaxies could have been scattered more randomly, or clumped even more tightly, leaving vast wastelands in between. Instead, we live in a universe balanced just so, structured enough to create stars and planets, but not so crowded that everything collapses too quickly. Our existence depends on this delicate balance, written into the very fabric of the web. Now, as we leave the filaments behind, picture one last view. The cosmic web from a godlike vantage, as if painted across the largest canvas imaginable. Glowing tendrils stretch in every direction, some arching into loops, others radiating outward, knots pulsing like lanterns at their intersections. Between them lie vast dark abysses, where light itself seems scarce. It is both beautiful and eerie, a reminder that the universe is not uniform but patterned, alive with a geometry that speaks of its beginnings and of its destiny. And yet, even this is not the end of scale. For between these filaments lie the great voids, stretches of near emptiness so vast they rival the filaments themselves in scale and mystery. To truly understand how big the universe is, we must now step away from the crowded highways of galaxies and drift into those silent deserts of nothingness, where the absence of matter tells its own story. We have wandered along the filaments of the cosmic web, those glowing highways where galaxies gather in clusters, knot themselves together into cosmic cities. But now, let us take a deep breath and step into a place even stranger, a place defined not by what is there, but by what is missing. These are the cosmic voids, the great deserts of the universe, where matter thins out almost to nothing. If the filaments are the veins of the cosmos, pumping with galaxies like blood cells, then the voids are the spaces in between, the silent, hollow lungs of the universe. When astronomers first mapped galaxy distributions in the 1970s and 80s, the discovery of voids was both unsettling and awe-inspiring. A famous example is the Boötes void, sometimes called the Great Nothing. It was uncovered in 1981 by astronomer Robert Kirshner and his colleagues. Imagine looking into a region of space nearly 330 million light-years across, yet finding almost no galaxies there. In fact, within that vast stretch, astronomers could only identify a few dozen galaxies, compared to the thousands that should normally be present. To put that in perspective, if the Milky Way were in the center of the Boötes void, our night sky would be eerily empty. with only a handful of faint galaxies twinkling in the distance. It would feel like living on a lonely island, surrounded by a dark, infinite ocean. Voids come in many sizes. Some are just 20 million light-years across, relatively small potholes in the cosmic road. Others, like the Bootes void or the Hercules void, stretch for hundreds of millions of light-years, swallowing regions larger than entire superclusters. These enormous cavities are not completely empty, of course. They may contain faint dwarf galaxies, lonely spirals drifting far apart, and plenty of dark matter. But compared to the crowded filaments, where galaxies cluster like stars in a night sky, voids are profoundly underpopulated. Let's imagine what it would be like to drift through one. At first, leaving the filament, galaxies would grow sparser. The great clusters would recede behind you, like city lights fading as you drive out into the countryside. Stars within the Milky Way would still shine all around you, but the grand external backdrop, the tapestry of other galaxies, would grow patchy, faint, and finally almost invisible. Ahead lies only the quiet. For tens, then hundreds of millions of light-years, you would cross almost nothing but blackness. The rare galaxies you'd encounter would be small, dim, and scattered like lone campfires in a desert night. The silence here is not just metaphorical. The density of matter is so low that encounters between galaxies, common along filaments, are almost non-existent. These galaxies evolve in splendid isolation, untouched for billions of years. The existence of voids raises deep questions. How can a universe that began with matter, spread fairly evenly, end up so uneven, with dense walls and empty bubbles? The answer lies again in those tiny fluctuations of the early universe. Regions that began slightly less dense resisted the pull of gravity. Matter flowed out toward the denser areas, leaving behind growing cavities. Over billions of years, those cavities expanded and merged, forming the vast voids we see today. In this sense, voids are not just empty. They are active participants in the cosmic dance, shaped by the same physics that built galaxies and stars. But voids are not mere gaps. They play a crucial role in the universe's story. For one, they accentuate the filaments. Without emptiness, we would not notice structure. The voids create contrast, like the dark canvas that allows the stars to shine. More importantly, voids act as laboratories for testing cosmological theories. Because they are so underdense, the effects of dark energy, the mysterious force driving the universe's accelerated expansion, may be easier to detect there. Voids expand faster than average regions of space, almost as though dark energy has freer reign inside them. By studying how voids grow and how galaxies within them move, astronomers can refine their models of cosmic expansion. There is also something profoundly philosophical about the voids. When we imagine the universe, we often think of stars, galaxies, nebulae, things that shine. But most of the cosmos is defined not by presence, but by absence. Voids remind us that emptiness is as fundamental to creation as fullness. The universe is not crowded everywhere. It is spacious, hollow, full of room. If it were otherwise, if matter were evenly spread, perhaps stars, planets, and life itself could not have formed. It is the very unevenness, the contrast of something and nothing, that makes existence possible. Let's return to the Bootes void for a moment, because its scale deserves lingering on. At 330 million light-years wide, it is so vast that if the Milky Way had been at its center, humanity might never have discovered other galaxies. The night sky would appear starry, yes, but all those stars belong to our own galaxy. Without nearby galaxies glowing in the distance, early astronomers like Edwin Hubble may not have recognized that the universe extended beyond the Milky Way. We might have believed, even today, that our galaxy was all there is. That's how much perspective depends on where you are in the universe. Not all voids are so barren. Some, like the local void near our own neighborhood, contain small galaxies on their edges. The Milky Way itself sits right at the boundary between a filament and this local void. In fact, the Milky Way and Andromeda are slowly moving away from the local void, drawn instead toward denser regions like the Virgo cluster. In a way, we are neighbors to the emptiness, living on the edge of a vast dark desert, but choosing instead to travel toward the crowded city lights of the cosmic web. Simulations of cosmic evolution often show voids growing over time. Matter continues to flow out of them, feeding filaments and clusters. This process makes voids ever larger and emptier. In the far future, as dark energy drives galaxies farther apart, the voids will dominate. Galaxies that remain gravitationally bound in filaments and clusters will cling together, but around them, the emptiness will balloon. Billions of years from now, a hypothetical observer in the Milky Way may find the universe has grown lonelier, the great walls fading beyond visibility, until even the nearest galaxies recede beyond the cosmic horizon. The voids will have swallowed almost everything. There is a strange comfort in imagining this fate. The universe, vast as it is, balances fullness and emptiness, crowding and solitude. We live not at the center of a cluster, nor lost deep in a void, but on the margins, able to glimpse both the crowded filaments and the silent deserts. Perhaps that gives us perspective, a sense of how rare and delicate our position really is. Astronomers today use voids to study more than just cosmology. They also probe galaxy evolution. Galaxies inside voids tend to be smaller, fainter, and bluer than those in crowded clusters. With fewer interactions and mergers, they grow slowly, evolving differently than their denser cousins. Studying void galaxies is like studying children raised in solitude versus those raised in bustling cities. The environment shapes their character. This diversity enriches our understanding of how galaxies form stars, build black holes, and sculpt their shapes. The voids also remind us of another truth. Space is not just big, it is mostly empty. Even in crowded regions, galaxies are far apart, separated by millions of light years of nothingness. At the stellar level, stars within galaxies are separated by light years, and even planets orbiting stars are mostly void between them. Emptiness is not the exception, it is the rule. Matter is the decoration. Emptiness is the canvas. Let's pause and visualize the universe once more. The cosmic web stretches like lace across the night, bright threads glimmering with galaxies. But between each thread is a hole, vast and black, like the negative space in a pattern. These holes are not flaws, they are essential. They give the lace its form, the stars their stage, and the galaxies their contrast. Without the voids, the universe would be flat, featureless, bland. With them, it becomes textured, living, and profoundly beautiful. So, as we leave the filaments behind and float into the cosmic deserts, let us not think of them as lifeless. Instead, they are part of the universe's rhythm, the inhale and exhale, the pause between notes that makes the music. Emptiness has its own kind of presence, its own role in shaping the great story of the cosmos. And though we cannot see it directly, its influence is everywhere, even here, on our tiny Earth, looking out at the stars. From the smallest void near our Milky Way to the vast Bhuta's void, these cosmic abysses remind us of something humbling. In a universe where even nothingness has shape, the meaning of scale takes on an entirely new dimension. Imagine standing on a quiet beach at night, the waves breathing in and out, the stars shimmering overhead like a silent choir of distant fires. You tilt your head back, and your eyes try to drink in as much sky as possible. The dome above looks endless, as though there's no ceiling at all. Yet, astonishingly, scientists tell us there is a horizon, an invisible edge to the cosmos that we can measure. Not a wall, not a curtain, but the limit of what light has had time to bring us since the beginning of everything. This is the edge of the observable universe, and its story is as much about time as it is about distance. Tonight, we journey outward, past stars and galaxies, to meet this horizon face to face. The observable universe stretches an incredible 46 billion light-years in every direction. That number sounds almost absurd, doesn't it? Light, the fastest thing we know, travels nearly 6 trillion miles in a single year. Multiply that by 46 billion, and your brain starts to wobble under the sheer enormity. But the most surprising part is this: the universe is only about 13.8 billion years old. So how can the edge lie farther than 13.8 billion light years away? That's one of the cosmic riddles we'll unpack tonight. To begin, imagine the universe as a vast rising loaf of bread in an oven. Galaxies are raisins scattered throughout the dough. As the loaf expands, the raisins move farther apart, not because they're zooming through space, but because space itself is stretching. Light, traveling through this dough, is carried along by the expansion. So while a photon may have set out billions of years ago, the very space it travels through has been stretching all the while. That means the galaxy that photon came from is now much farther away than when the light began its journey. Think of it like this. Suppose you and a friend are standing on a very slow-moving escalator that's constantly stretching apart. You toss a ball to your friend. It takes some time to reach them, but by the time it does, your friend is much farther away than when you first threw it. That's what happens with light in an expanding universe. The cosmic escalator never stops moving. When astronomers talk about the observable universe, they mean the sphere of space from which light has had time to reach us since the Big Bang. Picture a bubble around you with a radius of about 46 billion light years. That's the limit. Not because there's nothing beyond it, but because the light from farther regions simply hasn't had time to arrive. Imagine sitting in a theatre with the curtain only half open. The play might be grander than what you see, but you can only describe the stage revealed to you. This horizon isn't a fixed wall, it's more like a receding shoreline. Every second, as more light streams in, we gain new access to regions once hidden. But at the same time, because the universe expands faster and faster, some galaxies are being pulled beyond our ability to ever see them. It's as if you're standing at the edge of a desert, and the mirage of the horizon keeps sliding farther away, no matter how far you walk. Now let's dwell for a moment on what fills this observable sphere. At the center sits Earth, not because we're special, but because the horizon is drawn around every observer. If you lived on a planet orbiting a star in Andromeda, you'd also see a bubble 46 billion light years in radius centered on you. Every being, on every world, has their own cosmic horizon, just as every person has their own field of view standing in a meadow. Our horizon contains at least 2 trillion galaxies, each brimming with stars. If each galaxy were a grain of sand, you could pour them into buckets for lifetimes and never finish counting. And this is just the part of the universe we can see. Beyond the horizon may lie an infinite expanse, unmeasured and perhaps unmeasurable. In that sense, the observable universe is like a keyhole through which we glimpse only a sliver of a vast, undiscovered mansion. But let's circle back to the oddity of numbers. 13.8 billion years since the Big Bang, yet a radius of 46 billion light years. Here's the secret. As light was traveling toward us, the universe was expanding underneath it. A photon, leaving a young galaxy 13 billion years ago, might have crossed only part of that gulf before expansion pulled the galaxy farther away. By the time the light arrives at Earth, the distance to that galaxy has ballooned. That's why the observable radius is larger than the age of the universe in light years. The universe also places a limit on what we will ever see. Some galaxies are rushing away faster than light because space itself is expanding. That doesn't break the cosmic speed limit because the galaxies aren't moving through space. They're being carried by space. Imagine drawing 2 dots on a rubber band and stretching it faster and faster. At some point, the dots separate faster than any signal could cross between them. Likewise, beyond a certain distance, galaxies slip away from our sight forever. Their light, no matter how determined, will never reach us. There's something bittersweet in that realization. When we gaze into the deep sky, we aren't seeing eternal companions. Many of the galaxies in our telescopes are already lost, tugged over the horizon, unreachable even in principle. The observable universe is both a gift and a goodbye. a record of things as they were, not as they are now. Yet there's beauty in the thought too. Every night, when you look up, you're gazing across time itself. The faintest smudges of light you see with a telescope come from galaxies whose light began traveling before Earth even existed. The photons finally arrive after billions of years, touch your eyes, and vanish into the dark. It's a cosmic handshake across unimaginable distances. Now imagine what lies just beyond the horizon. Entire galaxies, star clusters, and worlds drift in that unlit ocean, hidden forever. Perhaps civilizations rise and fall there, just as invisible to us as we are to them. The observable universe feels immense, but in truth, it may be like a tiny island in an endless sea. The thought is humbling, comforting even. It suggests that no matter how far we explore, the mystery will always remain deeper still. Scientists use the horizon not only to measure distance, but also to test the shape and fate of the cosmos. By mapping galaxies and cosmic microwave background radiation, they can infer the curvature of space. Is the universe flat, curved like a sphere, or shaped like a saddle? Current evidence suggests flatness, which implies it could stretch forever. If so, the observable bubble is not a container, but just one patch in an infinite quilt. It's easy to feel lost in these vast numbers, so let's ground it in a mental walk. Start with the moon, 3 days away by rocket. Step farther. The sun, 8 minutes away by light. Then the nearest star, 4 years. The Milky Way across, 100,000 years. Now keep going. Andromeda, 2.5 million. The local group, tens of millions. The Laniakea supercluster, hundreds of millions. Then finally, the observable edge, 46 billion light-years. It's a ladder that climbs until the rungs dissolve into mist. And yet, you've made that climb tonight. Not with rockets or fuel, but with thought. In your imagination, you've walked to the boundary of the knowable, pressed your hand against the glass, and peered into the blackness beyond. That's the beauty of astronomy. It takes our finite minds and stretches them until they touch infinity. So as you lie there now listening, imagine yourself cocooned not just in blankets, but in an invisible sphere 46 billion light-years wide. That is your personal universe, your cosmic horizon. It hums with galaxies. It glows with ancient starlight, and it whispers stories from the beginning of time. Beyond it lies silence. Within it lies wonder. Both together make the universe what it is, boundless, mysterious, and endlessly inviting. Now take a slow breath. Let the air move in, like a tide filling a calm bay, and then let it slip away, as gently as a falling star fading from the sky. You've just journeyed through billions of light years, walked across cosmic ladders, and touched the horizon of the observable universe. That's a lot for any mind to hold, but you don't need to carry it all. You can set it down now, like a traveler resting their pack after a long adventure. Above you, the stars remain. They have burned for eons, and they will continue long after tonight. Each one sends its light across the deep, a quiet reminder that you are part of this great story, no matter how small you feel. Even the vastness, even the unreachable galaxies, are not there to overwhelm you, but to cradle you in perspective. You are part of a universe that sings, a cosmos that stretches without end, and somehow you belong right here, right now. Let your body sink deeper into where you are, your bed, your chair, your quiet space. Imagine you are floating in that bubble of the observable universe, safe inside, wrapped in 46 billion light-years of starlight. Outside the horizon, the unknown waits, but inside, there is peace. The waves of thought can calm now. The galaxies can rest. You've seen enough for tonight. The universe will still be here tomorrow, waiting for you, patient and endless. Close your eyes if you haven't already. Feel your breathing slow, steady, like the pulse of a distant star, and let go. Drift into sleep as softly as starlight crossing the dark. Good night, traveler.